Welcome to this session. We're going to talk about non-parametric statistics. This is a topic that is covered in Chapter 13 of the textbook. All of the parametric tests that we've studied so far, the t-test, the regression, or not regression, but the correlation, the analysis of variance, those kind of things, they've got non-parametric equivalents. And so we can cover a lot of these just by saying this is the equivalent to something that you've already looked at. The source video for this is 24 minutes long, and so I suspect that this will probably end up being at least 4 10-minute sessions or 9-minute sessions with the YouTube at least. So without any other further information from me, let's go ahead and get started on this. Up to this point in the course, with the exception of the chi-square, we've been talking about parametric statistics. Parametric statistics make certain assumptions about the parameters. What parameters, you might ask? Well, the parameters of the mean, the parameters of the standard deviation, the parameters of the distribution. Non-parametric statistics are not going to make the assumptions about those parameters. Sometimes they will be called distribution-free. That is, you have a population that's not normally distributed. You spend a lot of time working on getting this data, and you want to analyze it. So the parametric assumptions are not valid, and so the instructor or the researcher is forced to use something else, and that would tend to point to the non-parametric distributions or non-parametric test. So they're sometimes called distribution-free. The advantages of these are that they do not require the population to have a normal or a bell-shaped distribution. They can also be applied to categorical data, which would be nominal data. For example, if we were going to do a study of the types of shoe wear, we might have boots and sandals and shoes, regular shoes. And you could have flip-flops in there, you could have barefoot in there. How do you rank those? You can't really rank those, of course, unless you're in Texas, and then, of course, boots would be number 1. But those are nominal. They can't be ordered and get some sort of agreement there. Another advantage of the non-parametric is that many times the calculations are easier than they are with the parametric. Some of the disadvantages. One of the main disadvantages is that not all of the data is used. But if the data can't be used otherwise, but you can use it with a non-parametric test, then it's even better. When the data is ordered, sometimes you have to throw away the magnitude. It's not as efficient. So you need stronger evidence. And stronger evidence could be either a larger sample size or a greater difference. And again, as when we talk about efficiency, and I'll give you some numbers here on efficiency in just a minute, but as we talk about efficiency, that's the efficiency assuming that the parametric parameters are met, the parametric assumptions are met. If the parametric assumptions aren't met, then the non-parametric is more efficient than the parametric. So we'll use ranks. Now, majority of them use ranks. I'm going to do a couple of calculations here with the ranks. If we had the data of 1, 4, 6, 8, and 10, is our original data, we would rank that as 1, 2, 3, 4, 5. Okay? Rank of 1, rank of 2, rank of 3, rank of 4, rank of 5. So you can see that we throw away the magnitude of 10
and replace it with a value of 5. Now, if the data has ties in it, for example, it's got 1, 4, 4, 8, 10. So these two values here, the 4s, are tied. Then we go and we average those two ranks. This would be 1, 2, 3, so we average 2 and 3 to get 2.5. So this would have ranks of 1, 2.5, 2.5, 4, then 5 for these values. 1, 2.5, 2.5, 4, and 5. Efficiency. Let's look at the different situations that we might have. A one mean, if we were doing it with the parametric test, would be a t-test, and the sign test we'll talk about here in a few minutes, has an efficiency of 0.63. What does that mean? That means that if you had a sample size of 63 with the t-test, you would need a sample size of 100 with the sign test to get the same difference. Of course, assuming that the parametric assumptions are met. Now, a lot of these have got efficiencies 0.95, 0.95, 0.95, 0.91. There's not very much difference there. There's 5% difference. A sample size of 95 is compared to a sample size of 100. So while they aren't as efficient, they're almost as efficient. So it may be that that efficiency may not be a critical value or a critical parameter when you're going through and trying to figure these things out. So the sign test, the first one, is relatively easy to calculate. I won't go over that. The next test I want to look at is the Wilcoxon signed ranks for matched pairs. The parametric equivalent of that is t-test for matched pairs, paired t-test. Now, this makes the assumption that the differences are relatively symmetrical. So let's look at some data. We have some matched pairs here. Subject 1 has got a 78 and a 78, so there's no difference. Subject 2's got a 24 and a 24, there's no difference. Subject 3's got a 64 and a 62, so there's a 2-point difference. The Wilcoxon test, one of the things that we do is we remove those results that have a difference of 0. So we actually collected 16 data sets, but the Wilcoxon is only going to use 14 of those because it does not use those that are tied. So we go through 64 minus 62 is 2, 45 minus 48 is minus 3. We go through and we get the differences. And then we calculate the absolute difference. We just take the minus sign off of it. Minus 3 becomes a 3, minus 4 becomes a 4, plus 5 becomes a 5. Then we rank those differences. Again, the 2 has a rank of 1, 3 had a rank of 2, 4, there's 2 of those, so we average the 3 and the 4 to get a 3.5. Continue all the way down. This last number, 14, should match up with the sample size. Unless it's tied. If it's tied, then it'll be an average of the number previous to that and this one. Okay, I think that the 10 minutes are up, are getting close to for this first session. We're going to actually pick up with this in the next in the series.